Okay, this is day 2. Let's get started of Chemistry B Unit 7, Acids, Bases, and Salts. Oh my, we've talked about Arrhenius acids and bases, and today we're going to talk about Bronsted-Lowry. Before we get started on Bronsted-Lowry, I want you to watch a Brightstorm video on Bronsted-Lowry and what they are.
So let's talk about Bronsted-Lowry acids and bases. So previously we've discussed that there's the Arrhenius model of acids and bases, and then there's the Bronsted-Lowry type of acid and base, and that Bronsted-Lowry is more commonly now the definition that is used because it's more applicable, as the situation doesn't have to occur in aqueous solution. So basically the Bronsted-Lowry model defines acids and bases with respect to their ability to transfer protons. And we show protons here as H+. Okay, so that would mean a Bronsted-Lowry acid is a substance, either a molecule or an ion, that can donate a proton to another substance. Okay, so an acid with respect to Bronsted-Lowry is a proton donor. A Bronsted-Lowry base then is a substance that can accept that proton that was donated by the Bronsted-Lowry acid. Remember, acid-base pairs, they're paired because you cannot have one without the other. So here is the simple example. We have HCl, which is a strong acid, and water, which will go to form a hydronium ion and a chloride ion. Okay, so here HCl, because it's a strong acid, is our proton donor. And so here water is going to work as the base. And so remember, it's working as a base because it has this non-bonding electron pair that's going to come and remove this proton from the chloride, from the HCl. So that makes the H3O+, and then we have Cl- in solution as well. Again, remember, acids and bases work simultaneously to transfer protons between them. Okay, so the Bronsted-Lowry acid must have a hydrogen atom that it can actually lose as a proton, like HCl did, and the Bronsted-Lowry base, be it a molecule or an ion, must be capable of binding that proton via the non-bonding electron pair, like I just showed with water. Okay, so within that, there's this other type of definition that's important, and that's that substances can be amphiprotic, okay, and that means they can act as an acid or a base depending on the situation. So in the example I just showed you with water and HCl, water acted as a base. Why? Because water has the non-bonding electron pair and it removes the proton from HCl. Okay, so HCl acted as the proton donor, water acted as the proton acceptor. Okay, proton acceptor means that it acts as a base. In another example though, with water and ammonia, NH3, water is going to act as an acid, meaning that water is going to be the one that actually donates the proton. Okay, so let's look at that a little bit closer here. So we have ammonia is going to act as the base, because if you go back to your Lewis-Stat diagrams, you'll know that ammonia has this non-bonding electron pair on top. So it is going to go and remove a hydrogen from water to produce the ammonium ion, NH4+, and the hydroxide ion, OH-. Okay, so remember that water in specific is one of the ones that can act as an amphiprotic substance. And that is some more on acids and bases.
Okay, so acids and bases, Bronsted-Lowry. This is a new idea of what an acid and a base are. All right, his ideas will now cover a majority of the substances that are out there, the compounds. And Bronsted-Lowry says that acids are a hydrogen ion donor and bases are hydrogen ion acceptors. Okay. This new idea includes compounds which are also classified as Arrhenius acids, bases, as well as compounds which are not. So they encompass both. Conjugate acids and bases. Let's watch this on what conjugate acids and bases are. It's another Great storm video.
Hi guys. So let's jump into some more information about acids and bases, and let's specifically talk about conjugate acid-base pairs, which is kind of a prelude to talking about acid-base equilibria, and kind of a mixture of talking about equilibrium systems, which we should have already kind of encountered at some point. So remember again that an acid is a proton donor and a base is a proton acceptor when we're talking about this system. So in an acid-base equilibrium, both the forward reaction, so the reaction moving to the right, and the backwards reaction, the reaction moving to the left, involve proton transfer. So here I have a basic example of kind of an acid-base equilibrium problem. So we have HX here representing our proton donor, and water representing our proton acceptor. The double-headed arrows, right, indicate that this is an equilibrium. So the black arrow indicates the forward reaction, the blue arrow represents the backwards reaction. And so the products of this would be X minus is our proton acceptor and H3O plus as our proton donor. So what happened in the forward reaction is here water abstracted this proton, giving us X minus and H3O plus. Going in the backwards reaction, X minus abstracted the proton from H3O plus to make H2O and HX. Okay, so you might need to take some time to look at this separately to convince yourself of that. But here I have it written again that for the forward reaction, the HX acted as the proton donor or the acid, and water acted as the proton acceptor or the base. And then for the backward reaction, X minus acted as the acceptor or the base, and the hydronium ion, H3O plus, acts as the donor or the acid. So when you have in a system an acid and a base that differ only in the presence or the absence of a proton, we call those a conjugate acid-base pair. So the sample I just showed you in that particular instance, depending on which direction you were looking at the equation, the acid is HX, and then its conjugate base is X minus. So every acid has a conjugate base that's formed by removal of the proton. Okay, so again, in the previous example, X minus is the conjugate base of the acid HX. And then similarly, every base has a conjugate acid that's formed by adding a proton. So again, in the previous example, HX would be the conjugate acid of the base X minus. So here's another simple equation, so we can just kind of actually put in some molecules and see how it works. So we have NH3 ammonia acting as a base, and it has this lone electron pair. And we have water acting as an acid and forming an ammonium ion, NH4 plus, and OH minus. And so in this case, ammonia is the base, water acts as an acid, ammonium is the conjugate acid of the base ammonia, right? So this lone pair removes a proton from water, so we have the addition of a proton to make the ammonium ion, so to make the conjugate acid of ammonia. And then water is the acid in this case, and so it, when the proton is removed, becomes OH minus, the conjugate base. So the stronger the acid, the weaker the conjugate base, and the stronger the base, the weaker the conjugate acid. If you kind of think about that, that makes sense, because you can't have something being just as good at donating a proton as it is at receiving it. Otherwise, your system would kind of fall apart. And that's the basis of acid-base conjugate pairs.
Okay, so conjugate acid, particle which forms when a base gains a hydrogen ion. The conjugate base is a particle which remains when an acid has donated a hydrogen ion, H positive. Remember, you need to remember those. So the conjugate acids and bases are always paired with a base or an acid respectively. So here we go. Let's take a look at this reversible reaction where we have NH3 combining with H2O, and NH3 is the base and H2O is the acid. And we have NH4 positive is the conjugate acid paired with the base of NH3, and the conjugate base OH negative paired with the acid H2O. So conjugate base paired with the conjugate acid, conjugate base paired with the acid. Okay? Conjugate acid-base pair consists of two substances related by the gain or loss of a single H positive ion. Water is an example of a Bronsted-Lowry base. It's a hydrogen ion acceptor. Water molecule that gains a hydrogen ion becomes a positively charged hydronium ion. This is another one of those formulas that you are going to have to remember. H3O positive is hydronium. It is a water molecule that has gained a hydrogen ion. You need to memorize that. All right? And then there's a third type of acid and base. And yes, you need to know all three, the Lewis acids and bases. And this dude says, hey, acids will accept a pair of electrons during a reaction, while bases will donate a pair of electrons. Will donate pairs of electrons during reactions. Lewis acid is a substance that can accept a pair of electrons to form a covalent bond, and a Lewis base is a substance that can donate a pair of electrons to form a covalent bond. At this point, I want you to draw the formula on page 592. 592 of the Lewis acids and bases. And then right here we have a little bit of a summary for you. Okay? A little bit of a summary. Arrhenius, Bronsted-Lowry, and Lewis. These are the three acids and base definitions. Remember, for an Arrhenius acid, it is an H positive producer. For Arrhenius base, it's an OH negative producer. For Bronsted-Lowry, it is an H positive donor. And for a Bronsted base, it is a H positive acceptor. The Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. You will need to remember these. This little chart should be something that you study quite a bit over the next week or so, and certainly before the test, because these three questions, you will be assessed on all three of these, and what they do, what they accept, what they don't accept, and all that other good stuff. So that's today's lesson.